In this lecture, we're going to continue our straight line following controller. In a previous lecture, we developed the side-to-side control law to allow us to converge to the line in a lateral direction, meaning that if you project the line in the northeast plane down into the northeast plane, then the aircraft would follow that projection. And now we're going to converge to the desired altitude of the line. So if we go down, we talked about here what it means to follow that straight line. We designed that straight line, and then for the lateral tracking problem, we projected everything down into the northeast plane, and we were able to design a control law that sent this value E sub p to 0. Okay, so before we jump into the longitudinal control, we're going to note a couple things back from geometry, right? So the first thing we want to note is that we're going to calculate a projection onto the plane. But first we're going to look at calculating a projection onto a line. So let's go ahead and get started on that. So if we want to calculate a projection of, let's call it vector A onto a unit vector, we can note that, and we'll note that unit vector u. So let's draw this out. So we have a unit vector u, we have a vector A, and we want to project and find this point, this vector that I've written in red. So note here that it's along the direction of u, right? But it's going to have a different magnitude. It's not necessarily going to be a unit magnitude. So since our unit vector u has unit magnitude, we could write its magnitude as 1. Well, if we denote the dot product, so we're going to do this in 2 steps. 1, take the dot product for the magnitude, and then 2, combine that for the vector. So we're going to combine it with u. So if we look at A dot u, that's going to be the magnitude of A times the magnitude of u times the cosine of the angle between A and u. Right, so we'll define this angle right here as the angle between A and u, which then this just tells us that this is A times the cosine of the angle between them. So that'll give us our magnitude. So dot product is used to project and find that magnitude, and then that vector, let's call it A prime, is just going to be equal to then A times cosine of the angle between them times u, or this is just equal to A dot u times u, which is pretty cool. So we can project things down onto another unit vector really easily. All right, what if we want to project? Now, if we want to calculate projection of A onto a plane. Okay, so let's draw this out. So we have some plane here, and we have a vector A, and we want that A, and I'm going to draw this as a red line just to note this is the projection, and I'm going to call this S. So we want to know what S is. It's a projection of A onto the plane. Okay. Well, a plane is defined using a unit vector, or a normal vector. So this is a vector that's normal, and I'm going to actually say that I'm going to say it's a unit vector normal to the plane. So we have our plane, we have a point on the plane, we have this vector S, which is the projection of A onto the plane. And I want to note that basically S, from a high level, S is everything except from A, sorry, everything from A except the normal, the component of A that moves off the plane. All right, so that's just kind of a high level of what we're doing. So let's define everything. We have N is our normal unit vector. A is going to be a vector to be projected. And that's from the origin to be projected. And S is the projection. Well, using this concept here, that we want to project everything except for the component of A that's parallel, we can say that, or that's orthogonal, we say that S then is equal to A minus, minus, and we're going to do A dot N times N. Right, so this is everything in A normal to the plane. Excellent. So it's just as easy as that. We do A minus the stuff that's normal. So we have this vector that's defining the normal to the plane. So we use that to remove, we project A onto the normal and remove that from A to get to S. So now we can calculate a projection of a vector onto a plane, which is going to be one very helpful tool. Another thing we need to look at is similar triangles. So if I draw two triangles, well, let me draw it a little bit easier. Okay, so I'll call the sides of the triangles A, B, and C. And if I have a similar triangle, meaning that it has the same angles, has the same angles as the blue triangle. So the bigger one has the same angles as the smaller one, but the sides might be different. So A, B prime, and C prime. We can write a relationship that B prime all over A prime is equal to B over A. So now that's back from days of geometry. We have these similar triangles. So now going back to blue, say we know A, B, and C. So you know the sides of the triangle for the blue triangle. Then, and we know A prime. Then what is B prime? Well, just using simple math here, solving for B, right? Or B prime. B prime is just going to be equal to B times A prime all over A. Excellent. So we have two fundamental concepts. Now let's go use them. Just wanted to review that geometry for you. Okay, so let's now we're working on our longitudinal controller, meaning that we're trying to converge to the vertical component. Okay, so let's go through and define everything. So we have S. Oh, let me find my pen. S right here. S is the projection of E onto the QKI plane. So the plane that's formed by the vector Q and the vertical component of the inertial frame. Okay, so we have that projection. And one thing to note here is that it's going to be defined in terms of this normal, right? Where the normal we can define as if we go along Q. So if we take oh, it's weird in the video. We go along Q, cross it with, use the right-hand rule to cross it with the vertical. That's how we're going to get this normal. And note that since we're crossing Q with Ki is just equal to 0, 0, 1, right? That's going to be in the I frame. So that's going to simplify things just a little bit. And we'll get to that here in a minute. But anyway, so we can define the normal to our plane quite easily. Since it's the QKI plane, we just take Q cross Ki, and then we divide by the magnitude. This makes it a unit vector. So we get the unit vector out. And then over here, we have E sub P. This is, oh, I should have said this is EP. This is the same error vector as before, because we're doing just PI minus RI, and we have this relation right there. Okay, that's really good. So we've defined this projection. We have the error vector defined, so we should know what all of the vectors around here are. Okay, now we'll take this projected plane and we'll look straight at it, right? So this is the QI plane, and we can start to draw these triangles, and we'll use similar triangles, right? So if we look at this plane, we know, so if we recall, we have A, B, and C from our similar triangles discussion, right? If we look at vector Q, the component that's in that, that's pointing along straight along this axis is just going to be the northeast component of the axis is just going to be the north component plus the east component. Take this square of them and take the square root. So that's going to take care of the first two components of Q. And then this vertical component, if we're looking at it vertically, is just going to be our negative Q down. So we know the two sides of our triangle, and honestly we could get the third side of our triangle easily. We'd just do the square root of just the magnitude of Q, right? So we have a small triangle that we know everything in it. We know the two sides, so we know A and we know B. All right, now if we've projected our aircraft error down onto this plane, right? So this is the projection of the aircraft error onto the plane. Well, what we want to know is what height do we actually want to be, right? So if we look at this, just keep extending out our line Q, right, we would get to this point. This is our actual H desired. That's where we would like our height to be. Well, we know this component is this would be our A prime of the triangle, right? So again, this is our A prime. It's just going to be the north and east, the magnitude of the northeast component of that projection. And so then all we have to do is we have to solve for this guy, which we do on the next slide. Okay, so we just use our similar triangles. We use our similar triangles, and then we can solve for our desired height. Right, so this one, our desired height is that value, right? Negative r sub d, so that's our down component of the r vector. And this smaller component was what we get at, so this is going to now be a plus, right? hd plus rd, so that's this guy. This is what we called, right, b prime before. And this is what we called a prime. This is what we called b. This is what we called a. So using those similar triangles, we can just now solve for our desired height. Okay, so what we want to do is select our commanded height so that our actual height converges. So the goal, select our command such that actual height h converges to h desired. Okay, so that's our longitudinal tracking problem. And realistically, this equation right here now is going to be the most difficult problem, or most difficult part of this problem. So now if we were to look at here, this is our model for the autopilot. And the big key here is if we just look at this model and apply the final value theorem, then our height will converge, to either a steady state value, let me just say constant, or ramp value. So if this model for how height reacts to the commanded height, we can just give it a ramp, which is our line, right? And the control that we already have will get us to that desired value. So as long as it's just changing linearly like that, then we're good to go. So we can apply the final value theorem to our transfer function of the height, and we're good to go. So there's a couple other things that we need to worry about. First, let's see. So now we have, all right, so in this case, now we have our control signal. We're just going to let, so now we'll just let h sub c equal to h sub d. So that's going to be our control command. Okay, so before we finish up talking about this line following controller, we need a couple of tips. And this really should have gone in the previous video on this one. But we need the angle of our line, subtract our actual course angle. So this is going to help us know the error in course angle. This has to be between negative pi and pi. Otherwise, we'll end up moving in the wrong direction. Not that it won't converge, but it's just that you might take a really long loop to get around. So the book goes into that in a little bit more detail. This algorithm just talks about, this is just our wrapping function. So we're just wrapping that error, and then we apply the control. So this one is our error. And then we apply control. Excellent. So you just have to be just a little bit careful to make sure that your course angle error is between negative pi and pi. So you turn the correct direction instead of doing a full circle to go a small angle. And finally, I want to give a little bit of help on computing the cross product, right? So this comes into play right here, right? So we have the normal to our plane. Well, we can take advantage of the fact that we have a really simple vector for one of our vectors. So if we come down here, if we just look at, if you just recall, oops. That A cross B could be written in matrix form as A hat B, where A hat is equal to 0, A3, negative A2. We have negative A3, we have 0 along the diagonal, A1, and we have A2, negative A1, and 0. Okay, so if B is equal to 0, 0, 1, like we have in our system, or in our equation, then A cross B is just going to be equal to, it's going to pull off this 0, 0, 1 is just going to pull off that last column. So it's going to be equal to A2, negative A1, 0. So that just makes that just a tiny bit easier to calculate. And there you have it. Now we have our longitudinal control law with a couple of hints, and if we our longitudinal and lateral, and let's go back up to this line, and applying these two controls will allow our vehicle to converge to that line.